Alright, so this is section 6.10, which is on tests with categorical data. So in other books, this is also called chi-square test. Okay, so there are two kinds of chi-square tests. In this video, we're going to discuss what's called the goodness of fit test. Okay, so let's consider an example. So let's roll a die, unknown die, 600 times. And let's count the result. So the result could be 1, 2, 3, 4, 5, and 6. So the observed result, so suppose among 600 rows, 85 of them is 1, 95 of them is 2, 125 is 3, 110 is 4, 100 is 5, and 85 is 6. So let's just make sure the total is 600. So that's our observed result, and we want to show that the die is not fair. So that's our alternate hypothesis, and the null hypothesis will be the opposite of the alternate hypothesis, which says the die is fair. Okay, so we're going to perform a test on this. So the test statistic, because it's called a chi-square test, so the test statistic is chi-square. Chi-square is defined to be the sum of this quantity, so O minus E squared over E. Okay, so we want to know what O and E stands for. O is observed, the observed quantity. E is the expected quantity. So for example, if you roll a fair die 600 times, then the expected quantity should be 100, 100, 100, 100, 100, 100. Okay, so because this is chi-square, so we need to know the value of degree of freedom. Degree of freedom is the number of row minus 1. In this case, there's 6 rows because the die has 6 sides. So in our case, the degree of freedom is 5. All right, so let's calculate chi-square. So chi-square is the sum of O minus E squared over E. Good thing E is all equal to 100, so this is equal to, the first one gives you 15 squared over 100 plus 5 squared over 100 plus 25 squared over 100 plus 10 squared over 100 plus 0 squared over 100. This is not here. Plus 15 squared over 100. We put the calculator out. This is equal to 12. Okay, so chi-square equal to 12. Degree of freedom is 5. So let's look for 12 in row 5. So if you look at the row 5, 12 is between these two numbers. So the chi value, the p-value is between these two numbers. This means p is between 0.05 and 0.025. So because p is less than 0.05, we can reject H naught at 5% level and conclude that the die is not fair. All right, so let's do a different example. So let's move to the right. Okay, so suppose we want to model the waiting time for next vehicle appearing on the street. So we have a mathematical model that tells you what should be expected, and so this is theoretical value, and we did the sample, so this is the observed value. Okay, so we want to see if our model works or not. So H1 is asserting that the theoretical model is off or incorrect, and H0 asserts it's fine. Is not off. Okay. So same thing. To calculate the test statistics, we want to the test statistic is chi-square equal to the sum of O minus E square over E. So for the first row, it's equal to 5 square over 23. Second row is 10 square over 18. I'm not going to write down all the rows. Last row is 11 square over 19. It's going to press the calculator to find the value of this. This is equal to 21.4746. And the degree of freedom, so let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. So there are 9 rows. So the degree of freedom is 9 minus 1 is 8. So now we look for 8, the row number 8, and we look for number 21.4746. Notice that 21.4746 is between these two numbers, so the p-value is between these two numbers. So the p-value is between 0.01 and 0.005. In particular, p is less than 0.05, so we can reject H0 and conclude that the model, the theoretical model is off. All right, so let's do a new example. So let's erase all these. Okay, so let's we have seen this before. So if we toss an unknown coin, let's say 1,000 times, and we get 550 head and 450 tails, and we want to show this coin is not fair. So H1 is this coin is unfair, and H0 is this coin is fair. So there are two methods to calculate this thing. So we can use the method in section 6.2, or we can use the method in section 6.2, or use the method we just learned. Okay. So if we want to use the method in 6.2, then H1 means P equal to 0.5, and H0 means P is not equal to 0.5. Oh, the other way, sorry. H0 means P is equal to 0.5, and H1 means P is not equal to 0.5. And the null distribution is the normal distribution with mean being 0.5 and variance being 0.5 times 1 minus 0.5 over 1,000. Okay. So here we go, 0.5. And let's calculate what a standard deviation is. So 0.5 times 0.5 divided by 1,000, taking a square root of that. The variance is, the standard deviation is 0.0158. Okay, so that's 0.5, and our p hat, suppose hat is success, then p hat is 0.55. So the z-score is equal to 0.55 minus 0.5 over the variance, standard deviation. So this is equal to minus divided by 0.0158. This is 3.164. And after finding a z-score, we look for the table to find the, because it's a two-sided test, so we look for the area of two tails. So the p-value is equal to 3.16. 3.16 gives you 0.0006. 0.08, and because it's two-sided, so it's equal to 0.0016. In particular, P is definitely less than 0.05, so we can reject H naught and conclude the coin is not fair. Okay, so that's the old method. We can use the method we just introduced. So if we can use the chi-square test, head and tail, observed values are 550 and 450. So total is 1,000. So that's observed, and the expected value, if it's fair, it's going to be 500 and 500. Total still 1,000. So the test statistic is chi-square equals to 50 squared over 500 plus another 50 squared over 500. So this is equal to, let's see, 5 plus 5 is equal to 10. And the degree of freedom is equal to the number of rows minus 1. There are only 2 rows, so it's 2 minus 1 is 1. So if you look at the chi-square table, you will notice that the number 10 is not in the chart. Sorry, I lost the table here. Okay. So degree of freedom is 1, 10. So the number 10 is outside the chart. It's off the chart. And the rightmost value in the chart is 0.005. So this tells you that the p-value is less than 0.005, which is consistent with the method on the left. So in any case, same thing, because p is less than 0.05, we can reject H naught and conclude that the coin is unfair.